Okay, so when we left off yesterday, we were drawing different graphs, and we talked about the fact that your graph doesn't have to look the same as the graph beside you. Okay, these graphs are called isomorphic graphs, and all that means is they're the same graphs. They represent the same things, they just look different. So when you have these, both graphs can be labeled to have the same vertex and edge set. So if you look at number one, I already listed out your vertex set. You've got vertices of A, B, C, D, and E. What does my edge set look like for number one?
A
A to B,
to C,
B to C,
B to D,
B to D,
and E to D.
and E to D.
And C to D.
Good. And C to D. Okay. Is there a way that we can label this graph right here to represent this same exact picture?
What was the question?
Is there a way that I can label this graph with the letters A, B, C, D, and E to match this same exact information?
Yeah.
How? It's literally A, B, C, D, E. Okay. Basically, what they did with this first graph is they took A and E and just kind of stretched it out into a line. Okay, which smoothed everything out. Okay, double check yourself. I still have vertices A, B, C, D, and E. I still have a line that connects A to B. I've got a line that connects B to C. One that connects B to D. E to D, and C to D. So even though these two graphs look completely different, they are the same. Take a look at number two. What does my edge set look like for number two? A to B, B to C, C to D. Okay. A, B, B, C, C, D.
D to A.
D to A.
B,
You said what?
D, B,
D to B.
D to
Another D to A.
A to C.
And A to C. Okay. Take a look at this graph versus the second graph. Can I label the second graph to also represent this same exact thing? We can try. Can we do it?
No. No.
Sure, I'm sure you can.
Just
reverse
B.
We're A. It's like flip,
B.
right?
You don't have to flip this one. Let me erase all these lines here so you can see this a little bit.
Yeah,
Okay,
you
hold
can.
up. I think B would be at the bottom left corner, right?
You want B down here?
Yeah.
No, down here.
Left. No, I mean
Bottom
that
right
one,
corner.
that one.
This
that
one.
Yeah,
Okay, you want B here.
And then
And then you want, obviously, you want D at the opposite end of that line going through the middle.
So you want D here?
Yeah.
Okay.
I think C should be
No,
on
see,
left.
because that doesn't work.
No,
Yeah, it
D
does.
should be
Yeah, it
on
does.
D.
Never mind.
Let's label them and we'll check.
A
And then A is
A at the bottom
Yeah.
And then C is
and C at the top. Okay,
Yeah.
let's see. I need one that connects A to B.
Check.
Well, there that is. I need one that connects B to C. Well, there's that. C to D. Check. D to A.
Check.
Check. D to B.
Check.
Check. D to A. There's another one. And A to C.
Check.
Fantastic.
We are boys.
Okay. So now, what I want you to do is you've got 4 different pairs at the bottom of your page. Okay? I want you to look at these graphs and say, are they the same? If they are, then write yes. If they're not, write no. Look at all 4 of them and see if you can determine if the 2 graphs that are side by side are the same. I will tell you there is one that is not. Can you find it?
Probably.
Which one doesn't work? Think you found it, Trey?
No, I'm just trying to look over.
You look pretty pencil around.
But I think I got the one that doesn't.
I think you got the one that doesn't.
I think
Trey thinks he got the one that doesn't.
What's wrong?
Come on, you have something to do besides play the paper. Come on. No. What are you doing? Okay.
You come out here.
Huh? Yes, sir.
For this. Be one side.
No, it's A to C and then C to D. Anytime you get to a point, that's when you stop. Yeah, if that would have gone straight through like this, if without a dot there, then yes.
it's only one of them that don't.
There's only one of them that does not work. You said you're just gonna wait on me this time?
What?
You just,
Take a look at number one. How many do you think number one works? Good. Number one does work, okay? Basically what has happened in number one is they've stretched A out to this corner and B up to this corner, okay? Another way that I look at this and be able to tell, look at A. How many lines are coming off of A in this first one? 3. So when you come over to this one, you need to find a dot that has 3 lines coming off of it. Okay? So A has 3 lines, B has 3, D has
3,
C has.
3.
So each one of these have 3, so we can just go A, B, C, and D.
So that's really that easy?
It's really that easy. Okay, take a look at the second one. A has 3, B has, C has,
4.
E has, and D has. Okay,
That's
so
a
let's see.
two.
I've got a 3, a 3,
They're all 3.
a 3, a 3,
Oh, that was only 2 actually.
and a 2.
So those are- that was
So
one that doesn't
this
come out.
one does not work
Dang it!
because this has 4 and this only has 2. Okay, it would have needed an extra line here
Yeah.
to make this one work.
Well, we're going to use this.
Okay. So take a look at this one. A has 3, B has, C has, and D has 2. So I've got a 3 up here, a 3 down here, a 2, and a 2. So I can label this A, B, C, and D. And then finally, your last one. How many lines are coming off of each point? 2. Guess what? Each one of these are also 2. So you can go A, B, C, D, and E. So that's another way to look at these and tell whether they are the same or not. Question. Okay, let's finish the rest of our key terms in section 5.3. First thing we need to talk about is being adjacent. What does it mean to be adjacent?
Next to.
Side by side, next to. Okay, so we have adjacent vertices. These are 2 dots that are connected by a line. So something like B and C are adjacent. They're 2 dots connected by a line. B and D is adjacent. They're 2 dots connected by a line. So the other thing, and this is important, a loop is adjacent to itself. The loops are also adjacent. So if you look at the picture, is A adjacent to B? Yes. There is a line that connects the 2. This is a yes. Number 2 on the right, it says, is E adjacent to itself?
Yes.
Yes, there is a loop that comes off of E. Is D adjacent to A?
No.
No, there's no line that connects the 2. And finally, is C adjacent to itself?
No.
No. Question. Okay. Not only do we have adjacent vertices, we have adjacent edges. These are 2 edges that share a vertex. Okay. So something like AB and BC. Something like CE and ED. Okay. They share a point in the middle. Okay. So example 5 is AB adjacent to BC.
Yes.
Yes. I can go AB, BC. They share this point in common. Is CE adjacent to BD? No. CE cuts down like this, and BD cuts up like this. They don't share any points in common. This is not a point. There is no dot there. Okay, so this is a no. All right. This we've already kind of done when we were finishing up 5.2 there. A degree of the vertex is the number of edges at that vertex, or how many lines are coming out of your dot. So a loop counts as 2. Okay, you've got an exit and an enter. So take a look at this graph. How many lines are coming out of A? 1. So A has a degree of 1. There's 1 line coming out of it. B has a degree of 3. C has a degree of
2.
D is 2. E is not 3.
It's 4.
It's 4. Again, your loop counts as 2.
Okay.
Because look, you've got this one this one, and this one.
Okay.
So there's 4 here. Okay. We can also classify your vertices as an odd vertex or an even vertex. An odd one is just the ones with an odd degree. So your odd vertices in this graph are A and B. They don't have to have the same odd number, they just have to be an odd. Even ones then are C, D, and E. Not too bad. I think we've got 3 more terms. All right. A path, by formal definition, is a sequence of adjacent vertices from one starting point to an ending point. Okay. A path starts in one spot and ends in a completely other spot. So, your key here, though, is you can only travel an edge once. So once you go down a street, you can't go back up the street. Okay. So we need to find a path that starts at A and ends at E. So if I leave A, gentlemen, stop talking and pay attention.
You can't like turn in the middle where the lines.
You have to travel the lines. You have to go from dot to dot. So when I leave A, what's my only choice to go to? B. So I've got to go there. So now I'm at B. Where can I go now?
You can go to C or D.
You can go to C or D. So I can go to C and then to E. This is one path. A, B, C, E. Okay. You also told me I could leave A, go to B, and instead of going to C, I can go to D and then E.
Right.
This is another answer that would fulfill this example.
On a test, would you be looking for multiple answers?
I can take either or. It does not matter. That's what I love about this chapter. Because your answer can be different than yours, and you can be right, and you can be right. That's okay. Okay. The last thing we need to talk about is the length of the path. The length of the path is how many edges you've crossed. So if you look at your picture, we've crossed 1, 2, 3 edges in each one of these. Notice though, how many vertices did you write? 4. If you write 4, the amount of edges you have are 3. If you write 7, the amount of edges you have are 6. So, however many vertices you have, your edges are just 1 less every time.
That's legit.
Okay. So instead of going back and trying to count all this craziness, you can just go, okay, I've got 9 vertices, which means I have 8 edges. Okay? Circuit. A circuit is a type of path, but it's a special one. It has to start and end at the same vertex. Okay? Think about NASCAR. They go around and around and around and around. Okay? They always go back to that same spot over and over again. That is a circuit. Okay? So, example number 9. If I start at C, I need to go back to C. How can I go?
C, B, D, E, C.
You said C,
To B.
B, to D, to E, to C. Okay, that works. C to B, to D, to E, and back to C. How long is that circuit?
4.
Okay. You could have also gone backwards and started at C and went E, D, B, and back to C. It also has a length of 4. Okay. You could have left C, went B, D, E, went around E, and back up to C. That is also a circuit.
Doing what? Going around the loop?
Before you go back to C. Okay, so you could have gone down, across the D, down to E, around the loop, and back up to C.
Are we gonna have to write all of them, like, when we have questions like this?
Unless I say exhaust as many paths and, okay. Example number 10, find a circuit for E.
E to E.
Yeah.
E to E.
Yeah.
That's your smallest circuit possible. If you have a loop, that is a circuit in itself. You just leave E and go back to it. It has a length of 1. Okay. You could have also done back around all this, E to D to B to C and back to E. Okay. So again, there are multiple different answers. You may see a question on your test that says finding the smallest circuit. You always want to look for a loop then. Okay. They may say, I need a path with a length of 7. Okay. Those are the questions you're going to be looking at.
So if you ask the equivalent to 7, we would find a circuit that has 8 edges.
8 dots. You're going to touch 8 dots and cross 7 lines. Okay, so let's take a look at this practice. Okay, I'm going to do number 1 with you, and then I'm going to leave you off to do the next ones on your own and see what you can come up with. Okay, so number 1 says find a path from B to K. So I need to start at B and I need to end at K that goes through the point W but does not touch S. Ooh. Okay, so when I leave B, where can I go?
H.
I can go from B all the way across to H.
J.
Okay, I can then go from H to J
Why wouldn't you just go right to K from there?
because it says you have to pass through W.
Oh,
Okay,
okay.
so be careful there. You said from J I can then go to W
And then
and then you can go to K. Okay. So be careful with the wording. This one told you had to go through W. Take a couple minutes and try the other ones and see what you can come up with.
Okay.
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 Jenny.
One time. You ever seen that movie?
No.
For real?
Right. My husband finally bought Finding Nemo, so I guess I'll watch Finding Nemo for the first time in my life.
Oh, yes. My God.
He bought it so he could watch it with Riley.
You never seen Finding Nemo?
No.
That's crazy.
I finally just watched Finding Dory because it's on Netflix.
What's the point of watching Finding
Dory
Dory?
is funny.
If you never.
Yeah, if you never seen the first one, how can you just not watch Finding Nemo? How do you miss out on that?
Right. Just keep.
That was your childhood.
I guess.
My childhood was like
Still Forrest
Cinderella.
Gump, though.
I'm glad I
What
did.
about The Lion King?
Oh,
Would that be
My
considered
mom
your
never
childhood
seen.
or
My mom
mom's
never seen The
childhood?
Lion King.
Lion King's a little old for you.
I guess it came out like a year or two. before.
I don't like one. Can you pass to the same point twice?
Yes. You can go through the same point as many times as you want. You just cannot go across the same line once you've crossed it. So it's kind of like a one-way street. Once you go down, you're stuck there.
Would this be considered right?
Converse with your friends. See what they got versus what you got. I'm not against that.
I'm done, man.
Yes.
Wait, so would you have to do 5 letters to a length of 4?
Yes.
Okay.
We need 5 letters for a length of 4.
Wait, on a circuit, can you go back to the same line that you came down?
You cannot cross the same line twice. So think about it this way, when you cross the line, it burns, it's gone.
Oh, I can't do
Yeah, that one be.
So a loop counts as two, right? So it'd be B, B.
Yeah, like if you left E and went around the loop, it would be B.
Find a degree of each. For degrees is,
It's gotta be. Like, this is like two contractors. It's like this to this, but like those together.
Hey, he just left. Right.
what?
Like the one, like the ones you up, like you go outside.
The O is coming to Astros, two.
There's
Wait, this one.
It didn't crash.
You trying to cut this off? Something happened 3 years ago.
Oh.
No, not that. All she said was.
Oh, yeah.
Y'all smell that too, right?
Yes. It's like a cigarette.
Maybe go out here.
Smell like cigarettes.
Excuse me?
Nicotine.
Oh, stupid.
We ready to go over this?
Yes.
All right. So find a path with a length of 4 that goes from H to J.
Let me do
Let me
it.
do
Let me do it.
God.
Well, I have the next one.
I'm glad you can have.
That's bad. That's where it was stuck.
It wrong. Okay, that's why you can have this one.
I think I read the same thing you wrote.
Nah, I got it.
What'd you write? I missed it.
Oh, you slow.
Yeah, I read it
swear.
What
But
you
if,
do?
but if it was the,
It's
yeah,
an HJ, he did HKO.
if it was HTK, I would have it right. But I worked it out like H to J.
H to K to S, W to J. Good. Did anybody have anything different?
Let's see.
I put W in as,
That's fine too. That works as well.
No, that's exactly what I have.
and that's exactly what I had.
That. Okay, length of 5.
I can do this one though.
Got
I'll get it wrong.
it? He says, if I get this one wrong, I'm done.
Oh, no.
Listen, you're better off writing beside it, my friend.
All right.
That bottom corner is so hard to write in. Good. Anytime they're asking for a circuit of length 1, it's always your loop. Okay? Who's got number 5? You can just go up and mark the numbers by the dots.
Oh. Come here, baby. Oreo, follow. Right.
Good. Each one should have a degree of 3. Any questions? Okay. Let's finish this up then. We're about done, my friends. Okay. The next thing we need to talk about is graphs being connected versus disconnected. Okay. So a connected graph is where all pieces are connected somehow, some way. So there is a line that reaches out to each and every point. Okay. If the graph is disconnected, we call the different parts components. So in this one right here, we've got 2 components. This would be component 1 and component 2. And this is disconnected because there's nothing that's branching this piece over here to this piece over here. Does that make sense?
Wait. So is the graph 1 all just one component?
Yes,
Okay.
because it's all connected together. Okay. So that leads me into this. A bridge. A bridge is an edge that if I remove it, it takes my graph and it disconnects it. So if we go back, because they want us to do the bridge practice here. If we go back and you look at graph 1 that is all connected, give me a line that if I take it away, my graph becomes 2 separate pieces.
B.
BE.
Oh, yes.
I can take away B to E, and that creates 2 separate pieces. You've got this triangle up here and this little angle looking thing over here. There's 2 more. F to B is not one.
That's only one.
No, there's not. There's 2 more.
Man.
There is not.
Wait, what's the question?
And you're not thinking about it the way.
AB. Oh, no.
Wait a minute.
Wait, say
ED.
B to E.
DC.
Yeah.
What'd you say?
DC.
E to C.
Come on now.
Okay. E to C is also a bridge. Because watch what happens when I get rid of it.
It's gonna be a-
You've got this piece over here. Even though it's a dot, it is still part of your graph. So your dot is floating out in space while you have this piece that's all connected. Okay, so E to C is also a bridge. When you make an isolated vertex, that's also a bridge. So what's my last one then?
E to D.
E to D is my last one. Okay, so E to B, E to C, and E to D should go here. E to B,
It's always a
E to
twist.
C, and E to D. If you take a look at graph number 2, there are 4 bridges in graph number 2. Even though it is disconnected already, there are 4 bridges that make it even more disconnected.
SW,
SW,
WT.
WT,
U and V.
U and V,
TV.
and T and V. Okay, each one of these pieces here will make your graph separate into 3 components instead of 2. If I take away SW, component 1 is this chunk over here. Component 2 would be your S all by itself, and component 3 would be this chunk here. Okay, so each one of these lines is also a bridge. So we've got S to W, W to T,
And U to V.
U to V, and T to, is it T to B?
Yeah.
Okay, and T to B. So each one of those is considered a bridge.
Oh my God.
What are they doing?
So we have a couple more pictures that we're going to draw, and we're going to be done with notes for today. So, has 6 vertices and 6 edges. Where do I start in the
Hey.
first graph?
You're gonna start with a point, and it's gonna be A.
You don't even have to label them.
That's true. You don't even have to label them, guys.
How many dots do I need?
6.
I need 6. Okay, so start yourself off with 6 dots. And now I need 6 edges. Okay. It doesn't say that this has to be connected or disconnected. So you can draw it either way. Does not matter. So you just need 6 dots and 6 edges. Graph number 2 gets a little bit more specific. I still start with 6 vertices. I still start with 6 dots. I need to make sure that I have 2 bridges on this graph though. Remember, a bridge can simply be one that leaves a dot off by itself. So where do you want me to draw my lines?
Wait, like how many edges do you want?
Yep, it doesn't tell you how many edges you need.
Or you just,
I mean, you can draw the same.
You can do this. If I remove either one of those lines, I've disconnected my bridge. Because right now, with these 2 lines drawn, you've got 4 components, okay? You've got component 1, component 2, component 3, and component 4. If I go through and erase this line, this component breaks into 2. If I erase this line, this component breaks into 2. So those are considered bridges.
I feel like that's cheating.
I mean, technically, this is exactly what this is too. I've got 2 bridges in this picture. If I take away this one, this is off by itself. If I take away this one, this piece and this piece are separated. So that one works too. There's multiple ways to do this. And this is not cheating.
We're smarter, not hard.
Okay, right. Why reinvent the wheel when you can just tweak? Okay. Number 3. Number 3 should be super easy from yesterday. What do I need first? 4 dots, A, B, C, D. Okay. And where do I draw my lines?
A, B,
A to B, A to C, A to D, and B to D. There it is. Number 4. We need to start with 5 dots. P, Q, R, S, and T. Okay. And then literally follow the edge set. P to Q, Q to R to R means I've got a loop there. R to S, S to T, T to P.
Stone Temple Pilots.
Awesome. 2 more. Okay. This is where it gets hard.
Oh no.
I've got a trick for you. So I need 3 vertices that are even and 4 vertices that are odd. So how many total do I need?
7.
7. Draw yourself 7 dots.
7 things.
So We need to focus on how many lines are coming out of each. My suggestion to you is to make them all even first. And the way that you make them all even is you take your pencil and you literally play connect the dots around the outside. Okay? Don't connect anything in the middle.
Well, my dot's in the middle. So,
Okay, so draw a path from one dot the whole way through back. Like, don't go.
do this, basically.
You want to connect them all. Don't do anybody like. So let me put up what you have so they can see too. Okay, so Trey had a little bit of an issue because he put a dot in the middle. That's okay. Okay, so what I suggested to him was to do it like this. Even though he's got that dot in the middle, he can still play connect the dots. Okay, he just had to kind of make a V that went up into the middle then. Okay. So now, right now, if you've got a picture that looks like this, each one of these has a degree of 2. 2, 2, 2, 2, 2, 2, 2. We need to connect and make 4 of these odd. So I can take my pencil and connect one of the line or one of the dots across the center.
There you go.
So when I change this and draw this extra line, this now becomes 3. This side also becomes 3.
So
You've added an extra line. And all we need is one more line. You can connect any 2 points that you want. I can even go like this. And that changes this to a 3 and this to a 3. So anytime they tell you you need so many odd and so many even, my suggestion to you is always start with a bunch of even. Okay.
Oh, this number 6 looks crazy.
This number 6 does slightly look crazy. Okay, so they want us to do 2 separate ones with this. They want us to do part A, where we draw a connected graph. So I need 5 dots.
Do it 2 graphs.
Yes, you're doing 2 separate ones. We're doing one for A and one for B. Okay, I need 5 dots. I need 8 edges. As long as you have a line that goes out to each and every one of the dots, it's connected. Okay, so my suggestion to you with that, when you're looking to connect everything, pick 1 dot and connect it to every piece. That's how you should start. Because now, right now, your graph is connected. If you start at 1 dot and connect out to all of them. So how many lines have I drawn so far?
4.
4. Now I just need to add 4 more. So 5, 6, 7, 8. You can draw yourself a loop.
Oh, okay.
Okay? So your first job is to make sure it's all connected and then add whatever else you need to do. Okay? Part B then. I want the same thing. I want 5 dots to start. But this time, I want to leave a piece alone. Okay? So you can simply just make an isolated vertex. Don't connect one of your points, and it's disconnected. So just stick with 4 points and connect them with 8 lines. 1, 2, 3, 4. I can even do 5, 6, 7, and 8. Right? It's automatically disconnected because you left an isolated vertex. You could have also done something like this, where you connected these 3 and these 2 and just not connected those pieces. 4, 6, 7, 8. Okay? That's also a disconnected graph. So again, you can make these anything you want under the parameters. Question. I've got a worksheet for you to practice.